Ever feel like the universe is playing this cosmic game of too hot, too cold with complexity?
Yeah.
Stick with us, because today we're diving into complextropy,
Yeah.
a new way to kind of measure what makes things interesting. We're talking about going beyond just randomness or order and figuring out how to pinpoint that sweet spot, right, in between.
It really is a fascinating question. You see, we have this fundamental law in physics, the second law of thermodynamics, right, that says everything tends towards disorder, towards chaos. But then you have physicists like Sean Carroll asking, well, if that's true, then how come or why does the universe seem to become more complex over time, only to become less so later on?
Okay, so let's unpack this. We've got some fascinating source material to unpack, including this blog post called The First Law of Complexodynamics by computer scientist Scott Aaronson. And he dives into this idea using a really simple example, right? Imagine pouring milk into coffee.
Yes.
Super simple.
Yes, Carroll uses this analogy as well in his presentation.
Yeah.
You know, we intuitively get this feeling like that swirly in-between stage of mixing is more complex than both the initial separate liquids, the black coffee and the white milk, AD, the final, boring brown mixture. But how do you actually measure that? How do you quantify it?
Right. Because it's like our gut is saying that that middle stage is more interesting, but our usual ways of kind of measuring complexity don't really capture that, do they?
Exactly. If you look at just pure randomness, for example, we tend to think of random things as complex. But a string of truly random bits, for instance, is actually very simple to describe. You just say, it's random.
Yeah.
There's no real pattern there.
So how do we move past just randomness then?
Well, Aaronson dives into some alternative approaches to measuring complexity.
Okay.
So one that he starts with is Kolmogorov complexity, which is, it's a really elegant concept when you kind of wrap your head around it.
Yeah.
Imagine trying to write the shortest computer program possible to generate a given object.
The length of that program, in essence, kind of represents that object's complexity.
So like a simple object would have a short program.
Exactly. So a plain white square would have very low Kolmogorov complexity.
Okay.
The program to generate that would be super short, right? But something like a rainforest photo, teeming with detail,
Oh, yeah.
that would require a much, much longer program.
Precisely. And that's a good intuitive way to think about it. But even Kolmogorov complexity hits a snag when you apply it to, something like our coffee and milk. Because a program that would try to simulate every single particle to perfectly recreate those swirls
Oh, wow.
would become ridiculously long, right?
Yeah.
Even if the mixing process itself isn't that complex.
Right. Oh, well.
You see the problem.
So time to bring out the big guns.
Yes.
Aronson proposes this whole new concept he calls complextropy.
Okay.
It builds on this idea of sophistication that's used in algorithmic information theory,
Okay.
for our listeners who aren't familiar with that.
Right. So imagine you have this program, and it can generate random samples of milk and coffee arrangements, sort of like a cosmic barista. Sophistication basically measures how hard it is for a second program to recreate our specific coffee cup,
Okay.
the exact swirls and all.
So not just any cup of coffee with milk in it,
Right.
our specific one.
Using only the output from that first program.
Okay, so it's not just about whether something can be generated, it's about how well it can be recreated from like a limited set of examples.
Exactly.
Okay.
And there's another important factor here. Both of these hypothetical programs we're talking about,
Yeah.
they need to be efficient. They can't just take forever or use unlimited resources. This is really important because it reflects how we understand complexity in the real world.
Right, because in real life, we don't have infinite time to analyze every detail of everything, right?
And that's where Aronson's complextropy comes in. It's essentially saying it's not just about the randomness or the time it takes to generate something. It's about how efficiently we can describe both the process and the result.
So going back to our coffee, the most complex stage isn't just when the milk and coffee are randomly mixed. It's when those swirls and patterns
Yes.
are the most irregular and difficult to precisely describe. It's about the boundaries, the edges,
Yes.
the places where our simple descriptions fail us.
You've got it. And what makes complextropy so compelling is that Aronson believes this could actually apply to the universe as a whole.
Whoa. So instead of just looking at the universe's journey from order to disorder,
Right.
we're saying there might be this peak of complextropy somewhere in between.
That's the idea. And that raises some really big questions about where we fit into all of this, which we'll dive into right after this quick break.
So we left off with this idea that the universe might have a complextropy or peak. Are we saying that right now, as we sip our coffee and, like, ponder the cosmos, we could be at peak universe complexity?
It's a mind-blowing thought, isn't it?
It really is.
And while Aronson hasn't definitively proven it, right, his hypothesis is that the universe's complextropy, it follows a kind of arc, the very early universe. Low entropy, sure, but also pretty simple.
Okay.
And way, way down the line at the, predicted heat death of the universe. High entropy, sure, but also going to be low complexity. Just a cosmic soup of, like, evenly distributed stuff.
So everything interesting, galaxies, stars, planets, even life as we know it, it all happens in this middle period where the universe is neither too ordered nor too disordered.
That's the crux of it. It suggests that complexity itself, maybe even life, isn't just this fluke, but like a fundamental part of how the universe evolves over time. But, we need to be careful not to get ahead of ourselves here. Aronson is the first to admit that this is still very much a conjecture, something that needs a lot of further exploration and testing.
Right. So it's more of a launching off point than a definitive answer.
Yeah.
But it does make you think, what if there is this sweet spot for complexity, right? Could that change how we approach, like, all the information that's thrown at us every day? Is there a way to use complextropy as, like, a filter to figure out what's even worth our attention?
It's a really insightful connection to make. And it actually touches on another concept that Aronson grapples with in the blog post, which is this idea called logical depth.
Okay.
And this basically measures how long it takes for the shortest possible program to generate a given object.
So random bits would have very low logical depth because a program could spit those out really quickly, no problem.
Right, exactly.
But something with tons of structure, even if a short program could describe it, might take, like, ages to actually compute. Like, imagine a program trying to, like, simulate every brush stroke in a huge detailed mural.
A perfect example.
Yeah.
But Aronson argues that logical depth doesn't quite capture the essence of complextropy either.
Okay.
Let's think back to those milk swirls.
Okay.
A program simulating every particle's movement would take a long time to run, right? But there might be other programs that are much shorter, much faster, that could generate a visually similar image.
Right. So it's not just about the time it takes. It's also about how efficiently that program can, like, describe the complex thing, which brings us back to sophistication.
You got it. So sophistication in this context refers to the shortest program that can describe the set of possibilities from which our object is drawn. So for our coffee, the set would be all the different milk and coffee arrangements that still resemble our swirly cup.
And the more complex our arrangement is, the longer that program would need to be to accurately capture all the, like, possible variations within that set.
Precisely. So by adding this constraint of computational efficiency, Aronson basically takes sophistication a step further.
Okay.
And he gives us complextropy. But let's zoom out from the coffee cup for just a moment.
Okay.
How does Aronson connect all of us to the universe as a whole? He talks about how the universe starts in this low entropy state, right?
Right.
And it's headed towards this high entropy heat death. But where does complextropy fit into that timeline?
It seems like complextropy would have to peak somewhere in between those two extremes.
Exactly. Right? Think of it this way. The early universe, while low in entropy, was also relatively homogeneous. Not a lot of variation.
Okay.
And the eventual heat death of the universe, while high in entropy, will also be homogeneous, albeit in, like, a different way, right? Everything will be evenly distributed.
Okay.
But this middle period, that's where things get interesting.
Yeah.
That's where the universe is dynamic enough for things like stars, galaxies, planets, and even life to emerge.
You got it.
Right.
Yeah.
And it's such a compelling concept because it suggests that complexity, and perhaps even life itself, isn't just some, like, random accident.
Right.
But, like, a fundamental aspect of how the universe evolves over time.
Almost as if the universe is fine-tuned for complexity.
Now, that's a very loaded phrase.
Yeah.
And one that could spark a whole other debate.
Right.
But it certainly is a thought-provoking concept. And it leads us to a question that was actually raised in the comments on Aronson's blog post. Does this mean that higher dimensional systems are inherently less likely to be complex? What do you make of that?
Ooh, that's a good one. Yeah. I am thinking back to this idea of the edge of chaos, which I've come across in other, like, areas. Could that play a role here?
You're on the right track.
Yeah.
The edge of chaos basically suggests that complex systems often exist in this zone between order and chaos. Right. Too much order, and the system is too rigid, right? Too rigid to adapt and evolve.
Right.
Too much chaos, and there's just not enough structure for anything meaningful to emerge.
So the sweet spot for complexity is this like narrow band where there's just enough order for stability, but also enough chaos for like change and adaptation to occur.
Precisely. And the commenter on Aronson's blog post was suggesting that as you move into higher and higher dimensions, that edge of chaos, that perfect balance point, it becomes a smaller and smaller slice of all possibilities.
So are they saying that a higher dimensional universe would have less of a chance of having systems complex enough for life to arise?
That's the implication. And it's a fascinating thought experiment to, entertain, even if it's, purely hypothetical at this point.
I'm already picturing this vast multidimensional universe where pockets of complexity are these like rare and precious jewels.
A captivating image.
Mm-hmm.
And it speaks to the power of this whole exploration of complextropy, right? We're not just defining a new term, We're diving into these really profound questions about the very nature of the universe, the origins of complexity, maybe even the meaning of life itself.
Which is why we love these deep dives.
Yeah.
They take us on these incredible journeys.
That's true.
Starting with a simple question.
Right.
And ending up in places we never could have anticipated.
Exactly.
But let's come back to this complextropy idea. How can we, as listeners, apply this to our lives? What can we do with this information?
Right.
So we've been on this incredible journey through complextropy.
It really has been.
From swirling coffee to the vastness of the universe. And let's bring it back down to earth for a moment. How can we as listeners, actually use this idea in our lives?
That's the question, isn't it? It's one thing to sort of understand complextropy in the abstract, but how can it actually change the way we see the world around us?
Yeah.
The information we consume, the art we create.
Exactly. It feels like there's something profoundly useful here. And Aronson even kind of touches on this in the blog post. He mentions how some commenters they saw this potential for using complextropy to analyze music,
right,
or art.
It's a fascinating idea.
Yeah,
because it suggests there might be a way to objectively measure aesthetic complexity.
Wow.
So a piece of music that's both catchy but also unpredictable, for example,
right,
might have high complextropy.
While something that's either too repetitive or just pure noise would be less complextropy.
Exactly. It makes you wonder if there's some universal sweet spot for aesthetic complexity, something that just clicks with our brains,
right,
on a fundamental level.
It's a question that artists and philosophers have been debating for centuries. Yeah. But now we have this new lens, this concept of complextropy.
Exactly.
To maybe explore it in a more concrete way.
It really opens up some intriguing possibilities. Yeah. And I think it speaks to this broader potential for complextropy to be applied in, various fields. Think about biology, economics, even urban planning, anywhere where there's this interplay between order and randomness.
Yeah, it's really making me rethink how I approach information overload, honestly.
Yeah.
Maybe instead of just getting overwhelmed by trying to consume everything,
right,
we can maybe use complextropy to kind of discern what's truly valuable and worthy of our attention.
That's a great point. And it circles back to something that Aronson emphasizes, throughout his whole exploration of complextropy.
Okay.
Which is this importance of computational efficiency. It's not just about something appearing complex.
Right.
It's about whether we can actually describe and understand that complexity.
Yeah.
Within, real-world constraints.
Right. We only have so much brain power, right? Yeah. To dedicate to these things.
It's a good reminder that our perception of complexity is always filtered through our own limited cognitive abilities.
Totally.
There might be levels of complexity out there that we haven't even begun to grasp.
It's both humbling and inspiring, wouldn't you say?
Oh, absolutely.
It suggests there's always more to learn.
Mm-hmm.
Always deeper layers of complexity to uncover.
It's like that saying, oh, what is it? The more you know, the more you realize you don't know.
Yeah.
Or something like that.
Yes, exactly.
But instead of it being discouraging, right?
Right.
I think complextropy gives us a framework to kind of approach that vast unknown with a sense of curiosity and wonder.
Absolutely. And, on that note, I think that's a great place to maybe wrap up our deep dive for today.
I think so, too.
So, for you, the listener, the next time you encounter something that feels particularly complex and intriguing, whether it's a piece of art, a scientific theory, or even just a pattern you notice in nature, just take a moment to really consider what makes it so. Is it this interplay of order and randomness?
Yeah.
The efficiency with which it can be described? Or maybe it's something else entirely, something, we're only beginning to glimpse?
Keep those questions in mind. And who knows what incredible complexities you might uncover.
We'll be back next week to dive deep into more fascinating topics. Until then, happy exploring.